somewhat later and independently from Turaev, I would say. Okay, so let's start the talk.
Okay, can everybody hear me just okay?
Yeah, sure.
Okay, very good. So thank you for the introduction and thank you for the invitation. Let's just jump in and sort of give the plan. So the plan is to spend a little bit of time talking about the Turaev surface or atoms and define Turaev genus. And there's a somehow I made a typo on the first page. Okay, and give some historical background, just some where it came from and what's been done over that time. And then I want to spend the second part of the talk more focused on recent-ish work about how to relate, how to compute the sort of extreme terms of the Jones polynomial and the corresponding terms in Khovanov homology for Turaev genus 1 links. And then I'll discuss an application of that as well. Okay, so here we go. So the Turaev surface originally came from the proof, or a simplified proof, of the Tait conjecture for the crossing number of alternating knots. And I just want to kind of walk us through, I mean, everybody knows this already, but let's walk through what the original proof was, maybe at a little faster pace, but then talk about how the Turaev surface was used to simplify that proof a little bit. So we all know the Kauffman bracket. This is the format of it that I'm going to be using. And then it turns out that the span of the Kauffman bracket is a link invariant, right? The Kauffman bracket changes under Reidemeister 1 moves, but the span doesn't. And that span, by span I mean maximum degree in A minus the minimum degree in A. And it turns out that the top degree in A that appears in any of the state sums comes from the all A state, and the bottom degree comes from the all B state. And so that span is bounded. Those terms could cancel in general, but so the span's bounded by the difference that we have here in the second line, which is the first parentheses is the contribution of the all A state, and the second parentheses is the bottom contribution of the all B state. You do a little bit of sort of algebra in the last two lines, and it pops out to be what happens at the bottom: 4 times the crossing number minus this other term. Okay. And so Kauffman's proof, and to a certain extent Mursaugi's proof, although it wasn't exactly lined up like this, takes this, I have now gone backwards more than I want to do. Okay, takes this blue term that we have here and proves that it's always non-negative. Okay, so what Turaev did was he realized that this blue term was the genus of some orientable closed surface. All right, and so by recognizing that it was the genus of some closed oriented surface, of course, that means that it's always non-negative, an integer value. Whereas sort of Kauffman's proof was more just combinatorial in nature. Here's this number, let's prove that it's 0 or non-negative. Okay, so what we have, and then just to top it off, to remind us of the proof, that gives us this number 0 if the knot's alternating, and then a separate fact is that if the knot's alternating, the extreme terms don't cancel, and so the inequality becomes an equality, and that gives you that the span of the Kauffman bracket is 4 times the crossing number for alternating knots, and that since the span gives a lower bound on the crossing number, that solves Tait's conjecture, or at least that Tait conjecture. Okay, so here we go. So what's this Turaev surface, or the atom, and as y'all might say it. So the way that I like to think about it is you start by constructing a cobordism from the between the all A and all B states of the knot diagram, where there's saddles that correspond to the crossings, and then you cap off all the boundary components with cobordism of the cobordism with disks. And this is sort of wordy, and it's better to show it in pictures. So let's show it in pictures. So on the left-hand side, we have the A resolution, the B resolution, and on the right-hand side, we have the saddle that interpolates from the B resolution to the A resolution. I'm imagining that the knot diagram is projected onto the surface right there in that center part. So you can see the sort of projection of D sitting in the center of that saddle. And then you do this for every single one of the crossings, and then the sort of segments of the knot that go between the crossings are just bands. And you piece that all together, and it might look like something like this. So I think it's some 4-strand torus knot. I forget which one. It might be 4-6 or 4-7 or something. On the left, you have the all A state in the middle of the top and the all B state on the bottom. And then you glue together these saddles in the way that you have on the right. And that's almost the Turaev surface. To get the Turaev surface, you would cap off the boundary components with disks. And the all A state sort of lives above at the top of those saddles, and the all B state lives at the bottom of those saddles. And then it turns out that if you have a connected link diagram, the genus is exactly that blue term that we had before. So let's think about this for a minute. When you are looking at the picture, you have a way to give a cellular decomposition of this surface. And the 0 cells are exactly the crossings, right? So that's at the sort of center point of each one of those saddles. And then the 1 cells are the segments that run between the crossings, right? And so you have 2 times the crossing number of those, because the crossing, if you think of it as a vertex, is a 4-valent or degree 4 vertex. And then after that, you can just attach on the disks that come from the all A circles and the all B circles. And so the 2 cells correspond to the sum of the number of number of components in the all A state, number of components in the all B state. And so if you put all of that together, then you get this for the genus. And that was basically Turaev's observation, that this sort of term that was giving you the difference between the crossing number and the span of the Jones polynomial, or at least, and that inequality could be realized as the genus of this surface. Let's look at the surface just a little bit more. It turns out that the link, any link, has an alternating projection on any of its Turaev surfaces. So you have the link, and then you pick a diagram for the link, and then with that diagram, you construct the Turaev surface. And if you just look at the Turaev surface from one side, I guess it doesn't matter which side, but just from one side, and you follow the projection of the knot or the link on there from that comes from that diagram, it's going to alternate on the surface. And so what happens is, when you have in the original diagram, if you have 2 consecutive crossings that are non-alternating, so it goes over, then the surface is going to twist in between those 2 crossings. And when the surface twists in between those crossings, that means if you're just looking at it from one side, it'll go over, under, or under, over. And so that's what these 3 pictures are trying to show. The top shows what's happening sort of 3-dimensionally. The middle shows this twist, right? So the picture that you're looking at of the knot diagram on S2 might look like that middle picture if you ignore the Turaev surface. But then when you put the Turaev surface in, or at least that segment, you have the twist. And then when you untwist it, you get this, this alternating behavior. And that allowed Turaev to show that, that the genus of this surface was 0 when you had a connected sum of alternating diagrams, and only when you had a connected sum of alternating diagrams. So the idea of the proof was, well, if the genus of the Turaev surface is 0, then by the previous picture, you have an alternating projection to a genus 0 surface. So you're alternating, right? The reverse is that if a prime link is alternating, then when you draw out the all A and all B states, and I'll have a picture of this on the next slide, they just form the faces of the diagram. And so when you build the saddles that go between them, it's pretty clear when you cap it off, you're just going to get back the original projection sphere. So there's a little diagram. I think that's 6-3 and the light blue in the middle, and then the red circles are the all A circles, the dark blue circles are the all B circles. And you can see that you can cap off all of these, and I guess I forgot one in the sort of top left of the all blue circles here. But if you cap off everything, then you just get back the projection sphere. And so if you start with an alternating diagram, then you get the projection sphere back. And then there's just a little bit more to do that has to do with taking non-alternating connect sums of alternating diagrams. And you don't get back the original projection sphere, but you do sort of get back two projection spheres that you glue together in a weird way that gives you another sphere. So there we go. And then, all right, so that Turaev surface, at least as far as I know about, kind of sat there after this. And, you know, Turaev used it to give this simplified proof, and I don't know that it really got picked up on for a while. The next place I was aware it got picked up on was in 2007 by Dasbach, Fuder, Kalfagiani, Lenin, Stoltzfus. And so let me try and tell the story of what made them pick that up. So in Thistlethwaite's paper, the one that I mentioned earlier that proved the Tait conjectures, he shows that the Jones polynomial of an alternating link is basically just a specialization of the Tait polynomial of the checkerboard graph of that alternating link. There's like an overall term multiplied by t to some power and some sign in the front. And then a couple years later, Lou Kauffman figured out like, oh, I can define the signed version of the Tait polynomial, and then I can expand Thistlethwaite's result from alternating links to any link whatsoever. And instead of using the unsigned Tait graph, you use, or the checkerboard graph, you use the signed checkerboard graph. And what the group of 5 authors that I mentioned proved was that you can look at a ribbon graph polynomial that generalizes the Tait polynomial. And so this, at least I know this as the Bolobos-Reardon or the Bolobos-Reardon Tait polynomial. So that takes a graph that's cellularly embedded into a surface and defines some polynomial to it. And they proved that you can get the Jones polynomial, or really the Kauffman bracket, as some specialization of this ribbon graph polynomial. And the surface that the ribbon graph is embedded in is the Turaev surface of the diagram, or the atom of the diagram. And in their paper, this is when they first mentioned, all right, so we have this genus of this surface that we can associate to any diagram. Let's turn it into a link invariant in the obvious way. Let's just take the minimum genus for any over every diagram of the genus of the Turaev surface. So the GT of D here is meant to be the genus of the Turaev surface for that particular diagram. So this is, you know, 1/2 times parentheses 2 plus crossing number minus the number of components in the all A minus the number of components in the all B, and then you minimize over every diagram. And the Turaev's result in his paper, it wasn't phrased this way because he didn't define a link invariant based off of it, but it says that the Turaev genus of a link is alternating, is 0 if and only if the link is alternating. And so in some sense, you can view the Turaev genus of a link as being kind of like a measure of how far away from alternating the link is. And there's lots of measures that go along that way, but this is one of them. And then after Turaev genus was defined, well, I'll say something about the chronology here because it turns out the chronology is a little tricky and a slide or two. But there was a relationship between the Turaev genus or the Adam genus and Khovanov homology that was discovered by Vasily and then picked up and also kind of independently or rediscovered, maybe is the right word, by Shampanakar, Kauffman, and Stoltzfus. And just to set it up, this is how I'm going to talk about Khovanov homology. So for me, Khovanov homology is going to be a bigraded abelian group. And the way that I like to display the Khovanov homology is in these grids. And the column is indexing the polynomial grading or the quantum grading. The row here is indexing the homological grading. And then the entries in the grid are the entries that are just integers, are the ranks of the free part in each summand, and an entry that has a subscript is telling you that this is one summand of Z mod 2Z, right? And so this is, I think, is the positive 3-4 torus knot. It's Khovanov homology. And the thing that you use in Khovanov homology, the thing that was first used in Khovanov homology to tell you something about the Turaev genus, ends up having to do with the diagonals that the Khovanov homology lives on. And so if you notice, these look like slope 1 diagonals, but they're actually slope 2 diagonals because my polynomial grading skipped the even numbers here. And so we just define this diagonal grading as 2i minus j, and the red lines are indicating constant delta, right? So there's 3 different deltas there. And we define the minimum such delta grading and the maximum such delta grading where the Khovanov homology is non-trivial. And you can define the Khovanov homology width as sort of like the span of those delta gradings. We normalize by a half here because all of the delta gradings are either all even or all odd. And Vasily and then Champanikar, Kauffman, and Stoltzfus proved that the span, this homological width in the Khovanov homology -1 gives a lower bound on the Turaev genus. And the way I actually think about this, the proof of this, I think about it in terms of reduced Khovanov homology, but the Khovanov homology is sort of, there's more packages out there to compute actual Khovanov homology. And reduced Khovanov homology width is always 1 smaller than the Khovanov homology width. So there it is. And so just, I won't go through a formal proof of this, but I'll remind us at least how I like to think about it. In Thistlethwaite's paper in 1987, to get the relationship with the Tait polynomial, he said, all right, so when you're taking the Kauffman bracket, if it looks like you're about to disconnect the diagram in one of the resolutions, don't do that. Just leave it alone. And go to some other crossing. And if you do that, then at the end of your tree that you're doing with the resolutions, you're going to get a bunch of unknots that can be transformed into the unknot with no crossings just by Reidemeister 1 twist. So I'll call those twisted unknots. And the observation was that the set of twisted unknots has a 1-to-1 correspondence with the spanning trees of the checkerboard graph of the knot. And then Thistlethwaite was able to show that Tait's activity words, you could specialize those to get an evaluation of the Kauffman bracket. And so in some sense, on one side, you have the knot diagram or the link diagram and all of its twisted unknots. And on the other side, you have the checkerboard graph and all of its spanning trees, and the Tait polynomial evaluates over here to the Kauffman bracket. Now, Stefan Verily and then later on Champanikar and Kauffman realized that you could take this sort of spanning tree model for the Jones polynomial and lift it up to a spanning tree model for Khovanov homology. It's a little bit easier to state for reduced Khovanov homology. So for reduced Khovanov homology, each spanning tree or each twisted unknot, however you want to view it, generates a rank 1 generator in the spanning tree complex for Khovanov homology. And so you start off with a complex, or reduced Khovanov homology. So you start off with a complex whose total rank is the number of spanning trees and the checkerboard graph. And the differential is harder to define. It's not as easy to define as regular Khovanov homology, but that's the sort of price that you pay whenever you're doing these homology theories. If you come up with a complex that has very few generators, then chances are the description of the differential becomes more complicated, and vice versa as well. If you want the description of the differential to be very easy, then oftentimes you have to blow up the number of generators. And so it turns out that the spanning tree complex, if I could go back maybe a page or two, the spanning tree complex is oftentimes very, very close in its homological width to the actual Khovanov homology, especially for knots with small crossing number. And so what Champanikar, Kauffman, and Stoltzfus did was they took this whole spanning tree complex, and then they realized, oh, you, instead of viewing things as spanning trees sitting inside of the checkerboard graph, you could look at a certain graph that you would cellularly embed into the Turaev surface.
Hello?
And you can
Yes,
look
yes.
at,
Yes, excuse me. Yes, please. Your
Hi,
question,
Caitlin.
Professor Adams. Yes,
Colin, do you
please,
have
your
a question?
question.
Okay.
No question, so let's go further.
Okay. And so what they did was
Okay.
they realized that you could
Great.
take a,
The pharmacy is Walgreens in Williamstown.
Professor Adams, if you have a question, so please ask. Okay. Yeah, okay, let's go.
no problem. All right. So anyway, they saw a sort of symmetry between what was going on with the spanning tree complex and this other complex, this combinatorial way that you could associate spanning trees to graphs inside of the Turaev surface. And the diagonal grading happened to correspond with the genus of these embedded graphs. And so that's what gives us our relationship between the sort of width of the spanning tree complex of Khovanov homology and the Turaev genus. Okay. And so after they did that, I mean, I started at, Professor Stoltzfus was a professor at Louisiana State University, and that's where I did my PhD. And I'd started, you know, a few years before that and tried to get into, this was about the time I was getting into research. And there was this, at that time, there was a lot of questions about exactly how are Khovanov homology and knot-floor homology related, right? Like, what are the things that are true in one theory that are going to be true in another theory? And so they handed me this problem that said, we found this Turaev genus bound coming from Khovanov homology. Can you see what happens when you look at knot-floor homology? And it turns out that once you work through the technical details, basically the exact same proof works in the knot-floor setting. So the spanning tree complex for knot-floor homology comes from a different place, a different observation than the spanning tree complex and Khovanov homology. But you can still figure out there is a spanning tree complex. You can figure out what the diagonal gradings are, and you can just show that it corresponds, the diagonal gradings correspond to the same sort of thing they did in the knot-floor homology. A little added thing to this result, this 2007 result of mine, is that now you can see this result as a corollary between the two, or corollary to the spectral sequence that goes from Khovanov homology or reduced Khovanov homology to knot-floor homology. So that spectral sequence is known to preserve diagonal gradings. And that means that the sort of diagonal homological width for reduced Khovanov homology is always going to be at bigger than or greater than or equal to the corresponding thing for knot-floor homology. And then I followed that paper up with a joint paper with Oliver, where we kind of, I mean, frankly, these all could have been in the same paper, but I was just learning Khovanov homology and knot-floor homology at the time. Turns out that there's these invariants that come along with knot-floor homology, Khovanov homology, the concordance invariants, S of K, the Rasmussen invariant for Khovanov homology, and tau of K for knot-floor homology. And they come from special classes that exist in the homology theories. So they're essentially grading information on certain classes that exist in the homology. And you can take that along with some results of Thistlethwaite on the signature, and you can kind of show that at least inside of the spanning tree complex, there's always a diagonal that has grading that corresponds to tau. There's always a diagonal that has grading that corresponds to S. And there's always a diagonal that has grading that corresponds to, at least in my version, minus the signature. So, and
excuse me, I have a question.
Yes.
Sure. Having these invariants, so I had a theorem that if we reach the bound for the span of the Kauffman bracket, and if we reach the bound for the Turaev genus, then our diagram is minimal from the number of crossings. So do you have nice examples when we can compare Kauffman bracket span and one of many one of many estimates for G in order to get minimality?
So it's harder to do that for the ones that you have on this screen. The Khovanov one, there's adequate not to do the trick. And that's going to be a bullet point coming up. So if you're adequate, you meet this bound and the Khovanov homology exactly. And that's a result of Tetsuya Abe.
No. I think I wrote about adequate once, but about non-adequate. So we can use whatever invariant we have. I mean, so we can use any of those invariants to have something for those which are adequate. Yeah.
I've done, so I don't have a great answer for this. So there's sporadic examples where I've sort of noticed that it does satisfy and meet these bounds, and that then you can compute the Turaev genus. But I haven't been able to put my finger on, for this class of graph, these inequalities are strict, and if you're not in this class of graph, then they're not strict, right? They're equalities. And it is especially, I think it's especially hard to get a handle on what happens with this middle terms, because you have sort of tau and S aren't particularly easy to compute, and signature, while it's oftentimes you can compute it for infinite families. It doesn't always behave nicely when you try to do some little induction proof, right?
Yes, and also have you mentioned that the width of Higger-Floer also gives an estimate for the atom genus more or less because of the single circle states for the width?
Yes, so that is what I'm thinking of here.
Oh, okay, yeah.
Right,
okay.
GT of K for me would be the atom genus.
Yes, and one small remark for those who are not very familiar to that work. Actually, in order to estimate the atom genus, we should analyze the configuration of single circle states. So more or less, if we have an alternating diagram, then they are at the same distance from the A state. And that's why Khovanov homology is very thick. And the same can be said about the Higger-Floer homology, because there is a model for Higger-Floer and for the Alexander polynomial coming from Kauffman formal knot theory. So when we take a certain sum of single circle states.
That's perfect. So that basically describes the intuition behind the top result there. And so the middle result is essentially that same observation, but just adding in extra facts about where tau lives in this complex, in the Higger-Floer complex, where the Rasmussen invariant lives inside of the Khovanov complex. And then we had to prove a little something for signature that heavily relies on some prior work of Thistlethwaite. And then there's fractions of 2 in various places, essentially because people chose to normalize the grading slightly differently in Khovanov homology than in not-Floer homology. The advantages of the lower bounds in the middle one is that sometimes they can be easier to compute, right? Like especially if the knot is very close to some knot that is positive. So tau S and S both have really easy computations for positive knots. And then just to top this off, some really recent work by Seung-Won Kim and a couple of his co-authors, and who I think spoke in one of these seminars in the past couple of weeks, generalized the concordance lower bounds to many more concordance invariants using SLN homology and all of the Cavallo-Quilori slice torus invariants as well. So that's fairly recent work that Seung-Won did. And then we can use, of course, so I just listed a bunch of lower bounds for Adam genus. So how can we actually use those to compute things? So Abe and Kishimoto noticed that if you have an almost alternating knot or link, and so I'll write down the definition of this later on because it comes up. But the definition here that I'm using for almost alternating is the link is non-alternating and it has a diagram such that one crossing change will transform that diagram into an alternating diagram. And so if you have such a diagram, if you have such a link, then its Turaev genus is 1. And more generally, if you, instead of having one crossing change you to alternating, you count the minimum number of crossing changes that transforms your knot into an alternating diagram, then that's the de-alternating number that appears over here. And the Turaev genus is always less than or equal to the de-alternating number. Abe, in that same paper, Abe and Kishimoto proved for the 3Q torus knots, so T3, 3n plus 1, T3, 3n plus 2, that their Turaev genus or their Adam genus is n. And then I came in for a slightly later work and got the torus links, the 3, 3n. And the methods I was using generalized to closed 3 braids. And so we can compute the Adam genus for many closed 3 braids, and we can, I'll say, almost compute the Adam genus for the rest of them. And so what do I mean by that? I could compute the Khovanov homology lower bound for them. And then I could, once you have the lower bound, the name of the game is, all right, well, how do you come up with a diagram that meets that lower bound? And a lot of the times I could get a diagram that met the lower bound, and the rest of the times I got a diagram that was one bigger than whatever the lower bound was. So we knew that the Adam genus or the Turaev genus was either this or one lower than what we could realize. Abe then computed the Adam genus when L was adequate. And later on, with a group of undergrads at my school, we managed to compute the Turaev genus for torus knots, or some torus knots with 4, 5, or 6 strands. And that used the knot floor homology computations for torus knots. There's torus knots have lens space surgeries, and knots with lens space surgeries are more generally L space surgeries. There's an algorithm to compute the knot floor homology that just takes as the input the Alexander polynomial of the knot. And you can sort of follow that algorithm through to get the lower bound on the width of the knot floor homology. But then so that's sort of like half of the work. The other half of the work is figuring out what are the right diagrams of the torus knots that meet that lower bound. And it turns out that was fairly hard for us. There wasn't something that looked like it would naturally generalize from 3 to 4 to 5 up to n strands. So in particular, what you're looking at here is you're trying to take a torus knot and you're trying to find, by some notion of it, what's the least non-alternating diagram of that torus knot. And the standard diagrams of the torus knots are like very, very non-alternating. And so a lot of the work in this paper was sort of playing around with diagrams of torus knots to find ones that maybe meet the Turaev genus lower bounds. Okay. So we've learned a little bit about the Turaev surface. We're still sort of in the history section, just trying to say how it's been used. So the Turaev surface is a Heegard surface. That means it's closed oriented, and the complement of the surface is the closure of the complements is two handle bodies. And the link has an alternating projection to the surface. We already talked about that. And also, if you remove the projection of the link, then you get a collection, a disjoint union of disks.
Excuse me, can you provide us the reference to Junkan and Kim for SLN Rasmussen invariant?
You mean the reference for this paper?
Yeah.
Yeah, it's I can in 1 second. So it's called concordance invariance and the Turaev genus. And let's see. And I am now dropping it in the chat. My ability to get to the chat while I was screen sharing was slower than usual. It's been, I think, accepted for publication, but not published, but that's the archive link. Okay, are we good to go?
Okay, sure.
Okay. So we have here, we have the Turaev surface having these properties. Turns out that doesn't characterize the Turaev surface. You can take an example like this. So it's called it like a tilde T43 or tilde T4 something, because it's almost a torus knot, but not quite. And the idea is that you embed on the torus, and I'm thinking of this cylinder as being glued together at the top and the bottom so that it is a torus, like you normally would, but you take off the last the last three crossings, and you actually place them onto the torus rather than having them wrap around, and then you change one of them. All right, so I'm changing the crossing right here. And what this gives you is it gives you a Heegard surface where the knot is embedded on the surface in an alternating fashion. And if you take the complement of the embedding, you do get a disjoint union of disks that's checkerboard colorable. But because these knots are very, very similar to the 4Q torus knots, you can compute that the Turaev genus blows up, because I think the easiest thing to compute in this case is actually the middle lower bounds here, because each of the knots is exactly one crossing change away from a 4Q torus knot, and that gives you a way to either compute the S invariant and the signature invariant, or to come very close to computing it. So you know that those invariants can jump in a controlled manner as you do crossing changes. And since it's only one crossing change away from a torus knot, you can show that the Adam genus or the Turaev genus blows up as K goes to infinity. But they're all embedded on a genus 1 surface with all of these nice properties. And so as Colin would call these are toroidally alternating knots. So you need something more than just these conditions to characterize the Turaev surface, is the point of that example. One way to add something to characterize the Turaev surface was in a paper by Cody Arman, Nathan Dravinga, and Thomas Kendrick from 2014. And there's some technicalities here, and there's even some technicalities that I'm hiding that are in that fourth bulleted statement. But the basic idea is that if you, in addition to drawing the knot diagram on the surface that has these properties, it's a Heegard surface, so you can also draw its attaching circles, alpha and beta. And there's lots of different choices of ways to draw the attaching circles that would give the same Heegard splitting. But if they satisfy all these additional conditions, then you can guarantee that the Heegard surface you're staring at came from a Turaev surface, a diagram of the Turaev surface. So I don't know if this is super satisfying or not, because you're sort of trading the characterization as coming from a diagram in S2 to going to a diagram on a Heegard surface with special attaching circles that satisfy a slew of properties. In particular, I've thought about this quite a bit, and I haven't, I mean, this might be a deficiency of mine rather than something else, but I haven't been able to use this theorem in a way that furthered other things about the Turaev genus. But of course, that could be my failing.
There is a way of extending almost everything about atoms for the case of virtual knots when we have additional homology. And if we have a sort of Heegard diagram, so then we can ask, well, maybe we can do something for manifolds, for other manifolds, not just S3, or maybe even for S3, we can try to figure out some generalization of the Kauffman in bracket. So have you thought about that?
So I think you can take this definition and turn it into a definition for three manifolds relatively quickly. I don't know what to do with that definition. Like after you make the definition, you would like to sort of prove some theorems about it, you know, but I haven't been able to do anything with that. I do think this is, I think there's been a fair amount of recent work on diagrams in surfaces cross an interval.
Yes. So this is almost the same as virtual knots up to well, if
exactly.
we get stabilization. So surface cross an interval is just what we have for virtuals, and here we can take whatever manifolds, and so it would be nice to see whether a huge amount of results for virtuals can be extended to whatever three manifolds. So here, of course, we have to do Kauffman bracket, or maybe Wittgenstein Turaev or something like that.
All right, it's a very interesting question. Okay. Yeah, it really is, and it's somewhere that there's work to be done. I want to mention maybe one or two more things before we jump into really focusing on Turaev genus 1. So Effie Calfagiani gave this really nice characterization of adequate knots, and the Turaev genus plays a role in it. Garfalidis showed that for any knot, the span of the colored Jones polynomial, so my notation here is jk of n is the nth colored Jones polynomial. Probably you have to, if you're going to think of this result, you'll have to read Garfalidis's paper and see how he normalizes the colored Jones polynomial. That's something you have to do for every colored Jones paper. And he proved that the span of the colored Jones polynomial is roughly quadratic in the n that you're choosing, but the coefficients are these periodic functions that depend on n. And what Effie showed, Calfagiani, was that a knot is adequate if and only if at least the S1 and the S2 terms turn out to be, not periodic with period 1. And the first one is crossing number over 2, and the second one has to be this term that involves the Turaev genus and the crossing number.
Something like 2005, I had some work about estimating the atom genus, Turaev genus, for cables of the knot. So Kauffman bracket for cables is very much related to the colored Jones. So
right.
So I think we should compare, because, well, actually I proved that adequate knots. So we could estimate something for adequate knots. And here I think we should compare what they did with, well, it was an archive paper, not published, something like 15 years ago.
Yeah, that makes sense. So I think having the adequate knots realize these bounds is it's one direction that's really interesting, and I think your finger's on the right, like it comes from these cables. But the other direction, which shows if you meet the bounds in this certain way, then you are adequate. I think that's the big new contribution to Effie's paper here.
Well, actually, just a couple of words how I prove that theorem. Well, in order to, the idea is that, well, in order to decrease the genus by, say, 1, well, we have to increase the span of the Kauffman bracket by something. And if we look at the cable, in order to decrease the genus by something, by 1, we have to increase the genus by something more. And something is growing linearly and the other thing is growing quadratically. So that's, that means that for adequate knots, we cannot decrease the genus at all.
Ah,
So,
that makes sense. And
yeah, that was
that
my
seems
idea.
like it would be related to this, right?
Yeah, sure. So when I see squares, I just mean, yeah.
Yeah, very good. I will look back. I've read that paper that you said, but I've read it, 10 years ago. So I should read it again now that I know more things. Okay, so all right, I'm kind of done with my history and short history of where I've seen the Turaev surface, and I want to spend the rest of the talk maybe in greater detail thinking about Turaev genus 1 links. The very beginning is just going to talk about Turaev genus 1 diagrams and how they're related to almost alternating diagrams. So there's going to be a series of results that are essentially just playing around with diagrams, right? And then after we've done that and proven how to characterize Turaev genus 1 diagrams in certain ways, we can use those characterizations to talk about what the Jones polynomial and the Khovanov homology is for those links. And the focus is going to be, I guess, the real focus is going to be on the absolute extreme terms in this talk. I've also had some success thinking about the penultimate terms, but the proofs of things for the penultimate terms are combinatorially laborious enough that I probably won't present them in talks, right? They're in the papers. I'll tell you what the results are, but we probably won't slog through all of the proofs of those, and we'll focus on the extreme terms. So the first thing that I want to do is essentially give a picture of how to compute the genus of the Turaev surface, or really the diagrammatic atom genus, in a way that takes into account large swaths of a diagram being alternating, don't really do anything to the atom genus. So how do I, or to the Turaev genus of that surface? So how do I make that more precise? And that's by this notion of alternating decompositions. I first encountered this notion in a paper by Thistlethwaite, but the basic idea is pretty simple. Chop up the diagram into alternating pieces in some canonical way. And so the way that I'm going to do this, there will be pictures to show it, is you draw the knot diagram or the link diagram. Everywhere that you have a edge that's non-alternating, put 2 dots on it, and then connect the dots together with non-intersecting arcs inside of each face that go along the boundary, but not to the dot that's on the same non-alternating edge. So you go sort of here to here, here to here, and so on. And if you do that in every face, then you get a picture that might look like this, right? So connecting here to here, there to there, there to there. And this sort of splits up. I think Thistlethwaite calls these the alternating regions, which are the grayish regions, and the channel regions, which are the regions that are white here. And so you sort of chop up the diagram into these pieces that are alternating, and then you go between them, every time you go between them, you have a non-alternating edge. And I chose this example at first just to realize that the alternating regions don't have to be spheres. They don't have to be disks in the plane. They can be, here you have an annular alternating region, and you can have any planar surface as an alternating region if you make the diagram sort of complicated enough. Now I say that, but for the Turaev genus 1 case, it ends up being all disks. So this picture doesn't have the red circles in them, but you can imagine that the red circles are just the boundaries of this, whatever greenish blue color that is. So inside of each one of these shaded circles, you have an alternating tangle. Right, and you connect these alternating tangles together in a non-alternating fashion. And what happens is when you draw the all A and all B state circles, and you do it inside of one of the alternating regions, all you're going to do is trace out the faces inside the alternating region. And so just to go back to the picture, like one circle would trace out this face, one circle would trace out that face, and so on. And then when you cap those off with disks, of course, you're just capping off the alternating region, at least the faces that are completely contained within the alternating region. And so you can really think about building the Turaev surface by taking the alternating regions and just thinking of those as being planar surfaces, so disks or annuli or however many boundary components they need, and then connecting those together with bands that have to twist where the non-alternating edges are. And so your picture might look like this if you were doing it for this example. You would have a disk for the first and third that show one side of the surface, a disk for the second and fourth tangles that show the other side of the surface, and then you twist in between. And if you follow the combinatorics of that and make some arguments, then you can characterize Turaev genus 1 diagrams. So the way that the proof goes is essentially every prime Turaev genus 1 diagram looks like this thing at the bottom. And if you're not prime, then you can sort of take the spots where the diagram isn't prime, cut it, reglue it back in so that it looks like the thing on the bottom. So it's not that every Turaev genus 1 diagram looks like this, but you can sort of force every link that is Turaev genus 1 has a diagram that looks like this. So Cody and I proved this, and independently Seung-Won Kim proved this at the same time. Seung-Won Kim was a student of Ilya Kauffman, and is now in Korea. And now that we have like a picture, like every Turaev genus 1 diagram, or every Turaev genus 1 link has a diagram that looks like this, then that opens up the possibility of proving theorems about Turaev genus 1 links because we have this sort of standard format for them. Maybe some examples first. Of course, the thing that I've been showing you is an example of a Turaev genus 1 diagram. Non-alternating pretzel links are all Turaev genus 1. So like in this one, you have the first strand, first column is one of the alternating tangles, and the second 2 columns is the other alternating tangle. And I don't know if it shows up super well here, but some of the strands over here are sort of a lighter shade of gray, and that's meant to indicate that they are on the back side of that torus, and the darker ones are on the front side of the torus. And the torus in this case would be the Turaev surface. You can do something similar for non-alternating Montesinos links. And then I briefly mentioned this, but a lot of the proofs are going to focus on almost alternating links. So let's make sure we write down what I mean by an almost alternating link. So a non-alternating link is almost alternating if it has a diagram that essentially looks like the thing on the bottom left there. So you have this alternating tangle R, and you have one crossing that's outside of this alternating tangle. The pluses and minuses indicate like what the next crossing will be as you enter the tangle. So the minus indicates that when this strand on the top left comes in, the next crossing it hits, it will go under it. And Colin and a group of undergrads defined this in 1991. The crossing that's outside of R, we call the de-alternator, because it's the one that if you change it, you get an alternating diagram. And then here's on the right is a specific example. Inside the red dashed circle is the tangle R, and then you have the crossing up here that's the de-alternator. I think this is, I can't remember if this is positive or negative, but it's the 3-4 torus knot played around with a little bit to give it an almost alternating diagram. And then this is a slightly embarrassing question that I don't know the answer to, but I would really like to know the answer to it. So as I mentioned before, every almost alternating link has Turaev genus 1. We don't know if there's a Turaev genus 1 link that's not almost alternating. I highly suspect there is, but I don't have a tool to prove it yet. So, you know, I listed a slew of examples just now, and you might be saying to yourself, okay, well, let's just take pretzel knots and put them on arbitrarily many strands, you know, let the number of strands get bigger and bigger and sort of switch back and forth between alternating tangles in some fashion so that you know, this picture here has lots and lots, K gets very big. It turns out that for pretzel links, there's a way to modify the diagram so that they're all almost alternating. And that algorithm actually got lifted to Montesino links as well. And so Montesino's links are all almost alternating. The almost alternating diagrams of them are not standard pretzel diagrams or standard Montesino's links diagrams. Nevertheless, I still think it's probably possible to construct diagrams that are Turaev genus 1, but not almost alternating. One reason that this might be hard is the theorem that we have right here. And the theorem says that there's a sequence of mutations transforming every Turaev genus 1 link into an almost alternating link. So if you have, I'll prove this theorem in just a second, but let's think about this before we do the proof. If you have some candidate link that you think is Turaev genus 1 and is not almost alternating, at least in my mind, what you need to prove that it's not almost alternating is you're going to need clearly some invariant that can tell the difference between almost alternating and Turaev genus 1. And what this theorem says is that that invariant also needs to be able to detect mutations. So if the invariant doesn't detect mutations, then you're never going to be able to tell the difference between Turaev genus 1 and almost alternating.
We have a description of knots by rotating circuit diagrams. I mean, so we can rotate the circuit at each vertex and put plus and minus depending on whether you go to the right and go to the left. And then we have a sort of chord diagram, but in somewhat other sense. And actually, the Jones polynomial can be restored from such a diagram. And moreover, this diagram is something like, it has an intersection graph of the chord diagram, and we can restore the whole Jones polynomial from this intersection graph, and we can also restore the odd Khovanov homology. So there were some papers by myself, Denis Lyutko, and by Igor Nikonov, and actually this was the beginning of what we called graph links. So actually look at those chord diagrams. Maybe you can, try to check. Okay.
So let's prove this. In fact, I think a key step of this proof is an exercise in Colin's knot theory book. It's so close to an exercise in Colin's knot theory book that it might as well be one. So here's the idea. We start with, this is proof by picture. we start with the standard Turaev genus 1 diagram, which is some number of alternating two tangles connected together in a non-alternating way. And then I'm going to give you a series of mutations that shrinks the number of alternating tangles by 2. So the first blue dotted circle, you take that blue dotted circle and you flip it this way. So that's the first mutation, 180 degrees in the plane, like this. If you do that, then you get the second picture. And now you take the second picture and you're going to flip each one of those circles individually 180 degrees. And what you've done by doing those 3 mutations is you've just interchanged Ri and Ri plus 1. But now if you notice, the left 2 tangles on the bottom, Ri minus 1 and Ri plus 1, going between them is alternating. And so together they form one alternating tangle. Similarly, Ri and Ri plus 2, they form one alternating tangle. And so you've shrunk the number of alternating tangles in this picture from 2k to 2k minus 2. Okay, so you can just keep doing that until you get down to 2 alternating tangles. And then when you get down to 2 alternating tangles, you can do the trick that Colin and them did in the original almost alternating paper over and over again. You have a picture that looks like this on the left, and then you can take this top strand, the one that goes to minus minus, and you can wrap it around here. And if you do that, then changing the crossing that I have circled in red there will make this into an alternating diagram. And so what that says is you can do a sequence of mutations, and then you get yourself to a knot or a link, which is almost alternating by doing this extra bit. Okay, so we need a couple of more things about diagrams. I'm going to introduce adequate links here with a little more detail. I'm going to give away the punchline. So eventually we're going to be proving things about the extreme Jones polynomial coefficients and the extreme Khovanov homology coefficients. And for the most part, the answer is if you're Turaev genus 1, then you have at least one side of your Jones polynomial or your Khovanov homology that looks like the Jones poly or Khovanov homology of an semi-adequate link. And so let's remind ourselves what those are. You're adequate if when you take the all A state, the little arcs that come from the resolution, no 2 of those lie in the same component. B adequate the same way. I'll call a link semi-adequate if it has an A adequate or a B adequate diagram. Again, pictures are probably better. So this one is the 3-4 torus knot, the standard diagram is A adequate because when you draw the all A state and put in the little traces of the crossings, all of those have their endpoints on different components, right? It's not B adequate. I didn't draw that picture, but if you do draw the picture, you will see that you have some of the traces that end up on the same component on both ends. And what Seung-Wan proved was every Turaev genus 1 link is either semi-adequate or almost alternating. So let's walk through like a cartoon explanation of his proof with some details shoved under the rug, but here we go. This gives you the main idea. So in this picture, let's just look at the notation. The subscripts tell you which alternating tangle you start in. And I've drawn, so I've just named this top face W1 and the bottom face W2. And I've drawn every crossing that goes between W1 and W2. So this is just an example, but there's no crossings that go between W1 and W2 that are hidden inside of my tangle somewhere. I've made sure to draw all of those in the picture. And what happens is essentially his proof is essentially that the only way that you can force yourself, this picture, to not be semi-adequate after doing some reductions is if after doing the reductions, it looks like an almost alternating diagram. So what do I mean by those reductions? Well, the first thing we do is we just flight everything so that we get all of these crossings that I have drawn together into one region at the very beginning. This is similar to how you get the standard diagrams for Montesino's links. So you do all those flights and you collect all the crossings that go between W1 and W2 into one little twist region at the very beginning. And of course, some of those crossings go one way, some of those crossings go the other way. And so you should cancel them as much as possible. If you do cancel them, you get this picture. And then start to think about what the all A states and the all B states look like here. So the all A states in red, and I've just drawn a picture of it, as long as you have more than one crossing here, you're gonna not have an all A state that touches itself, its own component through here. If you have more than one crossing because you put a little circle here. Another way that the all A state will never will be adequate is if you have more than one, or I guess I should say more than two alternating tangles, because the only way for the all A state to have a self-incidence is if it happens where my cursor is and over here, where there's one crossing, except for this red state would have to wrap all the way around. And the only way for that to happen is if there's exactly two tangles. And then the blue state does have some self-crossings, right? So there we go. And if there was only one crossing and there are only two alternating regions, then one of the alternating regions would be the one crossing, and you would end up with sort of that picture on the bottom left. So that's an almost alternating diagram. Right, so there's details I didn't put in there, but that's the kind of cartoon proof that Seung-Wan came up with. And so the Turaev genus 1 diagrams split into almost alternating, or Turaev genus 1 links split into almost alternating links and semi-adequate links. Okay, so I made some claim that I want to prove something about the semi-adequate links, and about Turaev genus 1 links, and I want to prove that their Jones polynomial and Khovanov homology looked like the Jones polynomial and Khovanov homology for semi-adequate links. So that's good. And Seung-Wan's result says that the Turaev genus 1 links split between almost alternating and semi-adequate. And so what that means is that we can really focus on the almost alternating links, because whatever result I want is going to be true for semi-adequate. That's what we're modeling it off of. So how can we do it for almost alternating? And just to remind us, like an A-adequate diagram has monic Jones polynomial on one side. So first coefficient is 1, and a B-adequate has it on the other side. And I need to give some condition that's going to tell me which side this happens on for the almost alternating links. And you know, the condition came from the proof, right? So don't read anything into, like, I didn't go searching for this definition. We just looked at the proof and then made a condition based on that. So here's the idea. Take your D alternator, which is this crossing over here, label it U1, label the 4 regions around it as is. So the U1 and U2 are joined by an A resolution, and the V1 and V2 are joined by a B resolution. And then we're going to define the adjacent faces between U1 and U2. So let's suppose just we take a checkerboard coloring, and the U1 and U2 are colored with white, and the V1 and V2 are shaded. So what we look for is, in the diagram, we look inside of our tangle R, and we want to know how many, say, white faces share a crossing with U2 and a crossing with U1. And so over here in this picture, there are 2 potential white faces, the one that my cursor's in now and the one that my cursor's in now. And neither of them share crossings with both U1 and U2. So if you form a checkerboard graph, you're looking for a path of, you're looking for vertices that have U1 and U2 as neighbors in the checkerboard graph at the same time. So in this one, the adjacency between U1 and U2 is 0. But then if we do the same thing for V1 and V2, well, there's 5 faces that are in that checkerboard graph. There's the 2 up here, the 2 up here, and this one here, plus V1 and V2. But V3 is adjacent to both V1 and V2. And so adjacent V1, V2 is going to be 1 for this example. So I'm just defining some term here that's going to come into how we make A and B almost alternating. And so what we say is that an almost alternating link is A almost alternating if this adjacency between U1 and U2 is 0. And it's B almost alternating if the adjacency between V1 and V2 is 0. And then the theorem, it wasn't stated like this in the paper, but it was proved in the paper. We stated it like this in a later paper, is that every almost alternating link turns out to be either A almost alternating or B almost alternating. So you can always force there to be a diagram that has this either adjacency between U1 and U2 being 0 or V1 and V2 being 0. So let's prove that again, mostly by picture. I think I lay out the pictures first in oh, I said this already. This picture is A almost alternating because U1 and U2 have no adjacency. So the proof, and I'll go back to the picture as an example, is essentially you're playing off of the fact that the checkerboard graphs are dual to one another, the U checkerboard graph and the V checkerboard graph. And if the U checkerboard graph has lots and lots of adjacent faces, then you're forcing there to be lots and lots of, oh, my cursor's, sorry. You're forcing there to be lots and lots of faces that match up between U1 and U2. And if that happens, you're sort of breaking all the paths between V1 and V2. And so there can't be many paths between V1 and V2 if there are at least, there can't be any paths that are of length 2 between V1 and V2 if there are more than 2 paths of length 2 between U1 and U2. So that's the first statement. And that's just a playing off of the dual graphs. And then the last 2 statements require pictures to prove, and the pictures are coming. But so with the first statement, that means we know that we can limit ourselves to the case where the adjacencies between U1 and U2 and the adjacencies between V1 and V2 are both 1 or 2, right? If they're 0, then we're done. If one of them's very big, then the other one must be 0 and we're done. And so the question is, what happens when they're all 1s and 2s? And when they're all 1s, you can reduce to a smaller crossing, almost alternating diagram. And when one of them's 1 and the other one's 2, or the other one's 2, or both of them were 2, then it turns out the link is alternating. It wasn't an almost alternating diagram anyway. So let's show the pictures. So this is the case where the adjacency is 1 for both of them. So you can see, sorry, when I try to move my mouse, sometimes I'm scrolling on accident. So you can see with U1 and U2, this face is adjacent to both U1 and U2. The sort of big face here through this crossing with U1 and this crossing with U2. And you can also see V1 and V2 are adjacent, this crossing through V1, this crossing through V2. And the R1, R2, R3 are just alternating tangles, possibly empty. And what happens is that you can twist the R2 this way, twist the R3 that way, and you end up with pushing the 2 crossings that we marked earlier into a band, but they're opposite in direction, and so you can cancel them. And the red circle down there is again the almost alternating circle. And so this gives an almost alternating diagram of the same link with fewer crossings. So if both of them are 1, then you can reduce the number of crossings. And you just repeat doing that so that you're never in the both of them being one case. I think I just did one of them being 2 and one of them being 1. The case where they're both 2 is very similar. In this case, here's my almost alternating crossing. U1 and U2 are here, and the adjacent faces between U1 and U2 are here and here. V1 and V2 are there, and the adjacent face between V1 and V2 is here. And then you can just do these, you do a flight here and here to push the crossings here and here on the other side. And then you do an isotopy where you're sort of moving this down to here and pulling this one under to there. And the diagram on the right is now alternating. And so this, if you have one of them being 2 and the other one being 1, you're secretly had a diagram of an alternating link. So it wasn't almost alternating to start off with. And so that you do a similar argument for 2 and 2, and that allows you to prove that you always have at least one of these adjacency numbers being 0. Every almost alternating link has a diagram such that at least one of these is 0. And I've called one of them A almost alternating and the other one B almost alternating. So it's really just playing around with the diagrams. And then we just wanted a term. There's nothing fancy about this. Kim proved that every Turaev genus 1 link is either almost alternating or semi-adequate. Every almost alternating link is either A almost alternating or B almost alternating. We just proved that. Every semi-adequate link by definition is either A adequate or B adequate. So just put the A things together and put the B things together and have a name for it, which I called A Turaev genus 1 and B Turaev genus 1. Just mostly to make the statement of the theorem a little bit easier. Okay. So we're now entering the phase of the talk where we'll stop just playing around with diagrams and then ask, all right, we have the diagrams that have to have certain formats. Can we say something about the Jones polynomial and the Khovanov homology of those? Okay. I'm gonna take a sip of water. So if you start with an almost alternating diagram, and you resolve the d-alternator, then in either direction, an A resolution or a B resolution, then you get 2 alternating diagrams. And we know a lot of things about alternating diagrams. In particular, here's one theorem proved by Dasbach and Len, uses things from the Tait polynomial. I think it might have been a little bit later, but Stoimanov has a very similar theorem for adequate links. Just says that you can read off say the first 3 coefficients of or the last 3 coefficients of the Kauffman bracket or of the Jones polynomial of any alternating link with quantities that you can read from the checkerboard graph of the knot fairly easily. So I'm not going to dig into these proofs, so I won't belabor what all of these terms are, but I'll just tell you. V is the number of vertices in the relevant checkerboard graph. E is the number of edges in the simplification of the relevant checkerboard graph. So you take multiple edges and replace them with 1. Mu is the number of times you had to replace the multiple edges with 1 edge. So it's the number of crossings that live in the relevant twist region, number of twist regions basically that are bigger than 1 of a certain size. And tau is the number of triangles that are embedded in the graph. So it's just things that you can read off of the diagram. And you can see that the top term is plus or minus 1. So this is Kauffman knew this about the Jones polynomial of an alternating link right when he did the state sum. And then you have a second and a third term. And then Colin and his students realized that this top term, when you do the Kauffman bracket, so you do the Kauffman bracket, you resolve the d-alternator, you get 2 alternating links, right? One is the A resolution, one's the B resolution. So you do A times the Kauffman bracket of the A resolution plus B times the Kauffman, or A inverse times the Kauffman bracket of the B resolution. It turns out that both of those will have plus or minus 1 as their leading term. The leading terms will match up and they'll have opposite signs. And so the ones from the alternating resolutions cancel with one another in the Kauffman bracket. And you have, if you want to know what the non-zero terms are in the Kauffman bracket of the almost alternating knot, you have to make sense of what's happening with gamma 1 and gamma 2 here. So Oliver and I were able to do this for the first term in 2016. And then an undergraduate student of mine who's now a PhD student at Michigan State, were able to push this to the second term of the Kauffman, second coefficient of the Kauffman bracket of an almost alternating knot. So I'm stating these all for A almost alternating, but they have a sister theorem for B almost alternating. And the key here is that the thing that we do, that we get, is the number of adjacent faces minus 1 up to some sign as the leading coefficient, right? And we've already talked about that the number of adjacent faces is 0 for A almost alternating. And so you'll get a plus or minus 1 for that leading coefficient for A almost alternating. And then again, these terms, they're more complicated than the alternating case, which is expected, but they're things that you can read off of a graph. So P is this number of adjacent faces, and then like P0 and P2 have something to do with how many of the edges in that path of length 2 are multiple edges, and Q and S are some subgraphs that turn into triangles whenever you do the resolutions that get you down to the alternating diagrams. Okay. So once we were able to do this with the Kauffman bracket, we were able to prove some theorems about what the Jones polynomial had to look like. Again, this was a paper from Oliver and myself that did it for the leading coefficient and the trailing coefficient. And then Dean, Spiropoulos, and I managed to push it to a second coefficient. And what we proved is that if your Turaev genus 1, and here's your Jones polynomial, or we only write, the leading and trailing coefficients aren't 0, so we only start writing them when they're non-zero. Then the leading if you're A Turaev genus 1, then the trailing coefficient has to be absolute value 1, and the first and the second coefficient have to be opposite in sign, except for I allow them to be, they could possibly be 0. So either one positive and one negative, or one of them being 0. If one of them's 0, it has to be the second one, because I wouldn't have written the first one as 0. And then your B Turaev genus 1, that happens on the other side. And so the proof, we've basically done it, but let's just, at least for the first coefficient, again, I probably won't dig into the proofs for the second coefficient because they're not nice to talk about. There's just a lot of combinatorics that you have to run through. But let's sort of circle back and do it all. If you're A Turaev genus 1, then you're either A adequate or A almost alternating. If you're A adequate, then your trailing coefficient was 1 by Licorice and Thistlethwaite from the paper where they defined adequate lengths. And the proof of that is that there's only one state that lives in that for that degree of the Jones polynomial. If you're A almost alternating, then by the previous result, the coefficient is up to sign just, oh, I made a typo here. There should be a additional +1 to the V in the superscript. Your coefficient of your Jones polynomial, the leading one is this -1 to the V P minus 1, but that's just -1 to the V adjacency of U1, U2 minus 1. Since D is almost alternating, that's 0, and thus this gives you the absolute value of B1. There should be like a parentheses -1 with that. So the fact that we were able to show that every almost alternating diagram has this adjacency U1 and U2 being 0, gives us that this leading coefficient has to be absolute value of 1. And then we were able to use that. So there are 2 knots that when we came on the scene that were 11 crossings or smaller, that were whether they were almost alternating or not was in question. It's 11N95 and 11N118. It turns out that 11N95 has leading and trailing coefficients being absolute value 2. And so it can't be almost alternating. It can't be Turaev genus 1 either. For the second condition, where the first and second coefficients have to alternate in sign, we had to go considerably higher to find such a knot. If you look at this knot, the top coefficient is -2. All right, so that throws out being absolute value 1. And then the bottom coefficient is 1, but the second coefficient is also 1. And so those don't alternate in sign. And so that tells you that this has to have Turaev genus at least 2 and can't be almost alternating. And then this theorem was sort of the main point of why we went after the second coefficient in the paper with Dean Spiropoulos. If you have an M component link that's Turaev genus 1, where M is anything bigger than 1, bigger than or equal to 1, then its Jones polynomial is different than the Jones polynomial of the M component unlink, even up to multiplication by t to some power. So what this says is that there are no Turaev genus 1 non-trivial Jones polynomial. Non-trivial knots with Jones polynomial 1. So that's one thing it says. So this solves the Jones unknotting conjecture for the class of Turaev genus 1 knots. But it also says something about links. All right, the M equals 1 case is actually the hard part, and it's again sort of a combinatorial mess. What you do is you say, okay, you have 4 coefficients to play around with, the top 2 and the bottom 2, and the Jones polynomial, and you assume that 3 of them are 0. So that just told you a whole lot of information about what the checkerboard graphs have to look like, and then you just slog through the combinatorics on those checkerboard graphs and get something out. The M equals, the bigger than 2 case follows from the fact that the initial coefficients, the first 2, have to have the same sign. So as long as you have a multiple component link, the Jones polynomial doesn't alternate in sign for the unlink of that many components. And we proved that it has to alternate in sign for these links. And so what that does is it tells you that if you look at these links that are known to have trivial Jones polynomial, but they're non-trivial. So these came from Eliyahu, Kauffman, and Thistlethwaite. I didn't put a year here. I should have. I think it was early 90s, maybe mid 90s. These links have trivial Jones polynomial, so they can't possibly be Turaev genus 1. Okay. So if you work in with Khovanov homology, or you work with knot floor homology, basically anytime you prove a theorem about a coefficient of the Jones polynomial or a coefficient of the Alexander polynomial, you ask yourself, what's the lift of that theorem to the categorification, right? Can you strengthen that theorem by doing something in the categorification? And we know some things about the first and second coefficients of the Jones polynomial of Turaev genus 1 knots. So then it's natural to ask what happens in the first and second quantum gradings, or the first and second polynomial gradings for Khovanov homology of such knots and such links. So just to remind ourselves, we're going to be talking about Khovanov homology. So for me, I is always going to be the homological grading. J is going to be the polynomial or the quantum grading. Here's the same picture that we had before, and you can sort of recover the Jones polynomial. It's not quite the same thing. you have to multiply, you know, the way that the Khovanov homology was normalized was so that the Euler characteristic of the unknot gets t plus t inverse rather than just 1. So you have to do that to go between how I've been talking about the Jones polynomial and what the graded Euler characteristic of the Khovanov homology is. But you can handle those transformations. That's fine. Okay. And then I'm going to want to talk about gradings at the extremes. So you do mins and maxes, I min and I max is minimum and maximum. Homological gradings, J min and J max is minimum and maximum. Polynomial gradings, and then the delta min and delta max are the minimum and maximum diagonal gradings that we saw when we were looking at the width earlier. And there's a fair amount to this theorem. So Oliver and I, Dasbach and I together proved this one in 2018. We proved statements 1 and 2. And an in progress paper, which I hope to have out by July with a group of undergrads, proves the rest of the names, proves item number 3. And I just stated it for A-derived genus 1 links. What does this say? Well, we can read the first one as saying, all right, if you have an A-derived genus 1 link, then its Jones polynomial has to have the first coefficient being plus or minus 1. And so if you ask what's the natural lift to Khovanov homology, you would say in the minimum polynomial grading, the only thing that appears is one summand of the integers, rank 1 summand, nothing else. And so of course, if you have that, then when you take the filtered Euler characteristic, the graded Euler characteristic, you get back a coefficient of plus or minus 1. And we were able to lift that. The second statement says something about which diagonal that initial rank 1 summand has to live on. Effectively, it has to live on the middle diagonal.
Adam, excuse me, how, officially we usually stop at 8. So how much time do you need?
Okay. 10 minutes or 5. I can do it in 5.
Fine. Okay.
I'll do it in 5. Sorry. I was under the impression I could go a little long. Okay. So basically what I would want to show you now is just some examples of this theorem in action. And the third one says, okay, you can tell something about one higher up grading. So the gradings highlighted in orange are the gradings that we care about. And this is the 3-4 torus knot. It does live on the minimum diagonal. It is A almost alternating. And so this says we have a rank 1 summand here, and we have nothing in this one. So for this knot, its Euler characteristic has monic Jones polynomial, but the leading coefficients tell us that it can't be derived genus 1. For this link, the top coefficient's 2, so that throws it out. The bottom coefficient is 1, but it lives on the wrong diagonal. It's supposed to live on the middle diagonal. So this tells us it's not derived genus 1. And then there's one example here that uses the third part of the theorem. And the third part of the theorem is, all right, bottom entry's 2, so that doesn't work. It's supposed to be 1. Top entry's 1. Again, that's what it's supposed to be. But then if this was derived genus 1, the entry in the middle that's orange should be 0. So that's, it sort of lifts this Jones polynomial thing to the Khovanov world. And the proofs here use the scan exact triangle in Khovanov homology. And that's all I'll say.
Okay, thank you very much. I have a couple of comments. So first of all, it would be extremely interesting if we could judge about 2 knots which appear as cobordisms. So can we make any estimates on maps between Khovanov homology in terms of Turaev genus? So if we have some 2 knots with boundaries.
So I guess I would answer that with another question. I don't know much about this. Is it known that we can do anything with alternating knots?
No, well, I don't know.
Yeah.
I don't.
So the way I would approach such a problem is, in my mind, like Turaev genus 1 links are very close to being alternating, and their Khovanov homology is in fact very close to being alternating. And so if there was a statement that was true for alternating knots that you could then hopefully generalize for Turaev genus 1 knots, then that's how I would go. But I don't know of such a statement for alternating knots either.
Okay, that would be very nice to know. And also, just look at some papers by Professor Yon Jubé and by Pedro Manchon and I think by Roman Avdiev about estimates on estimates for penultimate coefficients, ultimate coefficients, and so on. Yeah,
So,
yeah.
One of Manchon's students. So Manchon did, with Bay and others, did this for the Jones polynomial, and one of Manchon's students, Maria, I'm blanking on her last name, did this for, did the Khovanov homology version of it, and has some work with Josef Shatitsky related to geometric realizations of the extreme terms sort of in the Khovanov homology.
Great. Dear colleagues, any questions, comments, remarks, please? Please, people are asking about your slides, so please provide your slides to us.
Yeah, no problem. I can email them straight away.
Great. Further questions, comments? Well, if it's not the case, so thank you very much again for a very interesting talk. Okay.
Thank you very much.
Thank you.
Thank you. Okay. All right. Thanks everybody for listening.
Thank you.
And I will send you the slides right after I sign off. All right. Bye, everyone.
Bye.